Okay, next up we're going to look at Jupiter, which is very different from the other planets we've looked at so far. All the inner planets in our solar system are what are called rocky planets. Mercury, Venus, Earth, Mars. They're solid. Some of them have an atmosphere clinging around them, but most of the planet itself is made up of, solids and liquids, and indeed mostly solids. But Jupiter, on the other hand, it's called a gas giant, and it's like all the rest of the planets in our solar system, Uranus and Neptune and Saturn, of course. These are all examples of what are called gas giants. And as a starting point, we can literally just think of them as a giant ball of gas. So they're not solid in the way that the Earth is or the way that Venus is. And so they're, in many ways, very different, very alien from what we normally would think of as a planet. Yet, at the same time, we're also going to see that there are some things that are very similar to what we have on Earth. And so that will be interesting, I hope. Now, here we see a somewhat scale-ish model of our solar system. Basically, this is showing the different planets, the gas giants and the inner planets. And so you can see the Sun is, of course, at the center of the solar system. Venus, Mercury, Earth, and Mars, they're all confined in these rings that are, relatively speaking, very close to the Sun. And then beyond that, you have the large asteroid belt, and that sort of separates the inner planets from the outer planets. And then you have Jupiter, which is much further away from the Sun, and then Saturn way far out, Uranus and Neptune very, very, very far away from the Sun, and then way out at the edge of the solar system is what's called the Kuiper Belt. Now, notice the spelling here, Kuiper. That's a weird name, but the way that you pronounce that is Kuiper. And the Kuiper Belt is this giant ring of debris at the limit of the solar system, and it has, everything from grain of sand size particles all the way to planet-sized particles floating around. And so that is sort of showing the sort of distances involved in our solar system and how it's laid out. Now, here we see some photographs of Jupiter. The one at the top left is one that's taken from a pretty decent telescope on the surface of the Earth. And you can see Jupiter here. You can even see the sort of band structure that Jupiter is famous for. We'll talk about that later. And you can also see the 4 Galilean moons here. You might remember we talked about how Galileo discovered that there were moons orbiting Jupiter, and that was one of the clues to him that the geocentric model of the universe, the idea that the Earth was the center of the solar system, that wasn't necessarily true, because here was things that were orbiting around Jupiter, not orbiting around the Earth. And so clearly the Earth was not the center of everything. Jupiter was prominent about its own moon system. Now, here in Part B, we see a larger image of Jupiter that was taken from the Hubble Space Telescope, which we talked about. That's the telescope that's in orbit around the Earth. It's above the atmosphere, so it does not have the light degrade by the atmosphere, and you can get really nice, sharp pictures from it. And of course, the most detailed pictures we have are from the probes that we've actually sent to Jupiter. And this photograph was taken from the Cassini space probe, which was actually a mission to Saturn, but it passed by Jupiter on the way. And it was able to take this and other rather stunning photographs of the planet. One other feature that you can see here very prominently is this red spot here. That's actually called the Great Red Spot. And that's a feature of Jupiter that is incredibly recognizable, and we'll talk about what that is later. Now, here is a list of some of its orbital and physical properties, and I just want to mention some of these. And again, we have this problem with these PowerPoints. It's not showing exponents, but this is 10 to the 27 power, so that's 1.9 times 10 to the 27 power. So that is, of course, in kilograms. And what's startling about this is that the mass of Jupiter has twice as much mass as all the other planets in the solar system together. You can take Saturn, Uranus, Neptune, Earth, all the planets in the solar system, add up all of the mass they have, and Jupiter is so big, so massive, it has twice the mass. The radius of Jupiter is 71,500 kilometers, and that's 11.2 times the radius of the Earth. So that shows you that Jupiter is big. And I'll remind you, just from your high school geometry, you might remember that the formula for the volume of a sphere, and Jupiter is roughly spherical shaped, is 4/3 pi r cubed. And so that size, at 71,000 kilometers, if we were trying to see the volume of Jupiter, we would get a cube of that, and it's just tremendously enormous. Now, you can also see the density of Jupiter is 1,300 kilograms per meter cubed. I'll remind you that the density of water is 1,000 kilograms per meter cubed. That is showing that the density cannot be rocky or metallic like the inner planets are, because the density of the Earth, for example, is much, 5 or 6,000, something like that. I don't remember exactly, but it's significantly higher because the density of rock is significantly higher. Now, we talk about the rotation rates of all the planets so far. We talked about, for example, how Venus rotates backwards, which was kind of weird, and it rotates very, very slowly. That Mars and Earth rotated about the same rate. When you want to talk about the rotation rate of Jupiter, it's a bit problematic because Jupiter does not have a solid surface where everything's rotating at the same speed. Instead, it's made up of basically a big ball of gas, and the different parts of this gas are moving at different speeds. And so in the pictures we just saw of Jupiter, I pointed out the sort of band structure. And so Jupiter has these sort of bands in it. And we're going to talk about this in a little bit more detail, but these bands actually move at different rates, and some of them even move backwards relative to the other ones. So you can't really talk about a single rotation rate of the mass of the planet. But what we can do is we can look at the way that the magnetic field of the planet rotates, and we can use that instead. And so based on the motion of the magnetic field, we can say that the rotation period is about 10 hours compared to 24 hours on Earth. Earth goes around its axis every 24 hours, so we say the rotation rate of Jupiter is about 10 hours. Now, here is a zoomed-in picture showing the Great Red Spot. And the Great Red Spot is basically like a hurricane. It is this massive storm on the surface of Jupiter. And what's really weird about it is that it's been there for a very, very long time. Basically, for as long as we've had telescopes to look at Jupiter, this storm has been raging on. Now on Earth, storms break and dissipate eventually, and even on Jupiter there are often smaller storms that do break up and dissipate over time. But the Great Red Spot, it has just been going for hundreds of years, and that's actually a startling thing to recognize. Now, I really like this picture because it shows something that is also, I think, rather amazing. And here we see a scale picture of the Earth. And so this is the size of the Earth compared to the size of the massive hurricane that makes up the Great Red Spot. And you can see that this storm that's been raging on Jupiter for hundreds of years is actually larger than the entire planet Earth. And I think that that's just astonishing just to think about that. Now, we talked about that sort of band structure that Jupiter has, and you can see that there are these sort of zones where these different bands are lined up, and you can see they get darker, they get lighter. It's how you can sort of distinguish among them. And we can see that these are caused by the convection kinds of currents that we talked about that drive much of the weather on the Earth. So here you have sort of the denser, cooler air sinking down, the warmer air rising up, and you can see that that creates this sort of mechanism for wind. And here we can see sort of the flow, that here's a band that's moving this way, and on either side of it is a band moving in the opposite direction. That's what we were talking about when we were saying that it's hard to talk about a rotation rate for the planet because these different bands actually move not only at different speeds, but sometimes even different directions. Now, if we define the way that the planet is rotating by how its magnetic field is rotating, we can use that sort of as a baseline to measure the motion of these bands relative to that. And that's what this graph is showing. And it looks pretty complicated, but it's actually fairly simple. And so let's talk about some of the features here. Now, on the vertical axis here, we can see that that's the latitude in degrees. And basically all that means at 0 degrees, that would be like the equator. And at 90 degrees, that would be like the North Pole of the planet. And here you can see on this grid, this is the 0 vertical line corresponding to the horizontal axis of velocity. So here is where there would be 0 velocity. And if you pick a band, so let's say I'm going to pick this band right here, I can see that that velocity, I can just go down, and that looks like something like 400 kilometers per hour. If I chose a different spot, if I chose, say, this spot right here, if I went down, I could say that the wind here is going at, I don't know, that looks like maybe 80 or 90 kilometers per hour or something like that. And so you can see that the speed of this band and that band and there are very different. Now, what's really interesting is if you look at the 0, some of these bands that are showing the velocity, this dark curve is to the left of the 0, which means it's negative. In other words, that's telling you that right here, the wind is actually going not to the right, but to the left. It's going in the negative direction. And so anything to the right of the 0 is going, the wind is going to the right. Anything to the left of the 0, the wind is going in the opposite direction. And so you can measure how fast a particular band is going and also what direction it's going from this graph. Now, the other question that you might wonder about is what is Jupiter made of? And it's mostly made up of molecular hydrogen, which is hydrogen bonded into H2, 2 hydrogen atoms bonded together. Remember, it's very difficult for hydrogen to exist just by itself. It usually likes to pair up with other hydrogen atoms. And then helium, which is a noble gas, and those are the 2 lightest elements on the periodic table. And in addition to hydrogen and helium, we have detected small amounts of methane, some ammonia, water vapor, etc. The interesting thing is that the chemicals that make up Jupiter don't account for the color. Those are not normally giving off those colors. And so we're not quite sure why Jupiter has the colors that it does. There must be some sort of complex chemistry that we don't yet fully understand. But the colors of Jupiter are quite pretty and very, very distinctive. Now here's that altitude, temperature, pressure graph that we've looked at so many times before now. And here is the version of that graph for Jupiter. Now what's interesting is that Jupiter does not have a solid surface in the same way that the Earth does. So when we looked at this graph for the Earth or for Mars, we said, okay, ground level is what we're going to call 0, and then we would go up the atmosphere. But Jupiter is essentially almost all atmosphere. So where do you call it 0? That is sort of the question. And somewhat arbitrarily, scientists have decided to make the 0 here be the place where the top of the troposphere lies. Remember, the troposphere is one of those atmospheric layers. We have the stratosphere. We've seen those layers on Earth as well. You can see sort of the composition of Jupiter's atmosphere. There are ammonia ice here. There's ammonium hydrosulfide ice. There's water ice. There's gaseous hydrogen, helium, methane, ammonia, water. All of these things are in these clouds. And that makes up what Jupiter is made of. Now, one of the things that is interesting is that the lowest cloud layers cannot be seen by optical telescopes. That's the type of telescopes that show visible light. And also, measurements by the Galileo probe show that the very high wind speeds that we see at the surface of Jupiter, on basically the top of Jupiter, the top of its atmosphere, they extend way down inside the planet. And so these wind speeds are probably due to some sort of internal heating. Jupiter has tremendous gravity, and so that gravity is a source of the internal heating inside the planet. But these things are not, very well understood, and that leads to a lot of different dynamics in the way that Jupiter's atmosphere works. And we can see that in the Great Red Spot that we've been talking about. It's existed at least for 300 years, possibly much longer. We just don't know. We've only had telescopes for a limited amount of time. And the color of the Great Red Spot, why is it red? How is it formed? How is it sustained? These are open mysteries. So there are a lot of things that we know, but there's still a lot of things that we have yet to figure out. And that's, for a scientist, is a very exciting thing, because every puzzle to be solved, that's why we do it. Now, we talked about how the Great Red Spot is basically like a hurricane, just a very massive hurricane. But what is a hurricane? A hurricane is essentially a weather phenomenon. And that shows that Jupiter experiences weather, and that's something that it shares in common with Earth. Earth has hurricanes. Earth has, for example, lightning. And lightning-like flashes have been observed. And so we've also seen, as I mentioned earlier, not just the Great Red Spot, but there are lots of other smaller storms that we have detected in the atmosphere of Jupiter as well. But they tend to be shorter-lived, and they eventually dissipate. So here we can see an example of that. Here are some smaller storms that have been imaged. This you can't really see it here, but this is not the Great Red Spot, but it's a similar storm. It was called the Red Spot Junior. Here's the Great Red Spot over here. You can only see sort of the corner of it, but this was tracked over different time, and so you can see that this storm was moving, and it just kind of sort of merged with the Great Red Spot and kind of got dissipated as it did. Now this last image is showing the comet Shoemaker-Levy 9, which in 1994, I remember this, I was in school and it was a big deal, it was in the news a lot, that this huge comet was actually, it basically crash-landed into Jupiter. And this comet, if it had struck the Earth, it would have been absolutely devastating to the Earth. But fortunately, it didn't strike the Earth, it struck Jupiter. And that was something that provided kind of a spectacular show. Now, here you can see at the top, you can see these fragments. Basically, that was caused because the gravity of Jupiter literally ripped the comet apart before it could strike. So rather than one giant comet smashing into the surface of Jupiter, it was more like a shotgun, a bunch of pellets hitting it. But if you remember, we talked about how tides work. And so on the Earth, if you have the moon and you have the Earth, we talked about how gravity depends on distance. And so the further away you are from something, the less gravity you feel from it. And so the moon, for example, is pulling on this side of the Earth harder than it's pulling on the center of the Earth. And it's pulling on the center of the Earth harder than it's pulling on the opposite side of the Earth. And that causes the Earth to sort of stretch out in these sort of tidal bulges. And it's stretched out kind of like a big ball of taffy. And so that basically happened to the comet as it approached Jupiter. The tidal forces, Jupiter's gravity on one side of the comet was stronger than the gravity on the other side, and it stretched it out and literally ripped the comet apart. Now, you can see here an image here. Oops. Let's try that again. You can see an image right here. This was actually the impact of the comet on Jupiter. So you can see just how much energy was released in that impact. And again, if that had happened on Earth, we would not be here to be talking about it, most likely. But anyway, we can see that was really a pretty amazing thing that happened, and it wasn't that long ago, so we were able to get pretty good data from it. Anyway, that seems like a pretty good stopping point, so we'll end this video here, and we'll go on and talk about some more features of Jupiter in the next video.